This is Predicting Viral Life History Traits, from Vaccine Resistance to Endemicity, presented by me, Nash Rochman, with co-authors Yuri Wolf and Eugene Koonin. The first part of this talk relates to our paper, Evolution of Human Respiratory Virus Epidemics, available on medRxiv and under review at F1000. The prediction of emergent variant characteristics remains extremely challenging. Faced with a new pathogen, it is desirable to be able to forecast the case fatality rate, CFR, into the future. It is often assumed that pathogens will evolve towards reduced virulence, but counterexamples abound, and considerable effort has been invested towards the development of a mathematical framework for predicting virulence evolution to clarify the landscape. Using a compartment model, with parameters tuning the degree to which symptomatic individuals are isolated and the duration of immunity, we chart the global phase space of viral life history traits for human respiratory viruses and identify where 4 different long-term outcomes are possible: disease-free equilibrium, endemic equilibrium, where a stable fraction of the host population is infected, unsustainable, a state of endemic equilibrium where the viral death toll exceeds the population birth rate, and crisis, where the host population experiences a rapid decline after the introduction of the pathogen. This phase space reveals kinetic constraints, where the variation of multiple parameters in concert leads to decreased CFR and increased pathogen fitness, whereas independent variation of the parameters decreases pathogen fitness. Smallpox, SARS-CoV-2, and influenza are analyzed as diverse representatives of human respiratory viruses. We showed that a reduction in CFR for highly virulent viruses, such as smallpox, is likely often constrained by host behavior, whereas for moderately virulent viruses, such as SARS-CoV-2, there appears to be a constraint imposed by the relationship between the duration of immunity and CFR. Furthermore, we demonstrate that at endemic equilibrium, moderately virulent viruses can lead to a large disease burden, shown by the red data, comparable to that of much more virulent viruses, due to a much larger stable infected population, shown in the black data. The next portion of this presentation relates to our paper, Substantial Impact of Post-Vaccination Contacts on Cumulative Infections During Viral Epidemics, available on medRxiv and also under review at F1000. When the immune population is rapidly expanded through vaccination, more specific, short-term predictions can be made in the face of dramatically altered selective pressures, and optimal vaccine distribution is constrained by the potential emergence of vaccine resistance. Analogous to chronic low-dose antibiotic exposure, recently inoculated individuals who are not yet immune play an outsized role in the emergence of resistance. We constructed a separate model with compartments defined by the relationship to the emergence of vaccine-resistant mutants, representing 3 susceptible populations, 3 infected populations, and 1 recovered population. We then sought to identify conditions minimizing the cumulative number of infections. When an escape variant is much less infectious, represented by beta is much less than 1, than the originating strain, delaying the onset of vaccination, measured by the fraction of the population that has already been infected and since recovered at the beginning of the vaccination effort on the y-axis, or decreasing the rate at which vaccines are distributed on the x-axis, increases the cumulative number of infections, represented by the color, reported relative to the cumulative number of infections without any vaccination attempt, as expected. However, when an escape variant is only modestly less infectious than the originating strain, there exists an optimal rate of vaccine distribution, and exceeding this rate increases the cumulative number of infections due to vaccine escape. Analysis of the model also demonstrates that inoculated individuals play a major role in the mitigation or exacerbation of vaccine-resistant outbreaks. Modulating the rate of host-host contact for the inoculated population, represented by Q on the y-axis, by less than an order of magnitude can dramatically alter the cumulative number of infections, represented by the color, reported relative to the cumulative number of infections without any vaccination attempt. Consideration regarding limitations on post-vaccination contact remains relevant for the entire duration of any vaccination campaign, including the current status of SARS-CoV-2 vaccination. Thank you for listening. Thanks to the support from the Intramural Research Program of the NIH, and thanks as well to the ISCB and SysMod for the opportunity to present.